Okay, hi everybody. Welcome to vSphere Distributed Switch Design Best Practices. Just like to introduce myself. I'm Dan Watson, and this is my colleague over here, we'll just call him Venki, yeah? I won't try and pronounce his name. So we'll get straight into it. So firstly, actually, before we start, it'd be good for us to get an idea of where everybody is in terms of using our distributed switch or using our standard switch technology. So just as a show of hands, who in the room is or knows whether they're using distributed switch? Okay, all right, good. It's a good show of hands. In terms of where you are technically, are you network team or VI? So people who are VI, more on the vSphere side, put your hands up. Okay, network people, core networking. Oh, that's good. Okay, so we've got a splatter in a network team as well. That's great. Okay, so what we're going to talk about today is really the new capabilities, a little bit about new capabilities. We're going to do about 15 minutes on that, and then we're going to hand over to do some design and best practices, which Venki is going to take over for. Okay. So, firstly, there are some sessions that you can go and see. There's some hands-on labs. It's worth going into the hands-on labs and doing the design best, or the vSphere distributed switch hands-on lab, which will go through how to migrate and some of the new features in 5.5. So that'd be worth going to. And there's some other sessions as well. So if you want to write maybe those down, maybe pick up some of those other sessions as you go through the week. Okay. So the agenda as such. We're going to do an overview of features, and as I say, we're going to look at customer deployment options, how you could deploy it in your environment, and then we're going to go more into design and best practice. And then we'll have a quick answer, question and answer session at the end. Okay, so let's look at the features. First of all, for you who are not familiar with the distributed switch, I mean, the main concept is that with the VDS, we can span multiple hosts with one configuration. Yeah, so we build a virtual switch that spans multiple hosts rather than it being centric around one physical host. And rather than having to recreate all of that work on every single host to build your virtual switch infrastructure, you do it once within vCenter. And we'll describe that in a little bit more detail. Also with the VDS, different from the standard switch, is that a lot of the new features that we're bringing out are only based on or only implemented in the distributed switch. So it gives you a reason to move up the stack, move towards Enterprise Plus to get some of these new features. And obviously scale as well. So we're now looking at the sort of scale where we can span 1,000 hosts with a distributed switch. So we have huge scale, huge amount of hosts that we can cover, and so there shouldn't really be any scalability issues with the distributed switch. And really the important thing here is that as you move forward, you've probably heard a lot about NSX already. Show of hands if anybody hasn't heard of NSX. Okay, that's good. So everyone's heard of NSX. This is extremely important from an NSX for vSphere perspective. Everything that we're doing in NSX is based on VDS. Okay, so that's the foundation for your NSX journey. Okay, so let's take a look at the architecture of the VDS. First thing to say is that the VDS is based on a management and I/O plane. Okay, so we have a management plane for configuring VDS, and we have an I/O plane. So from a management perspective, we configure a virtual distributed switch within vCenter. So all of the functions are built into vCenter for creating that distributed switch. It's very similar to a standard switch in that it's got port groups where we define our teaming policies and our VLAN tags, etc. within our port groups. But then we create it once at the vCenter level, and then we add hosts to it. So underneath we can see that we've got two hosts, two vSphere hosts. Each of those hosts are then added to the distributed switch. As we add that to the distributed switch, what effectively happens is that configuration is pushed down to each host. So rather than you having to go to every single host and configure your VLAN tags per port group and ensure that all of your naming conventions are correct, otherwise vMotion fails, etc., we can do it once at the vCenter level and push that down. Okay? Now there's some things at the side that you can see, the port groups. We have port groups exactly the same as you would in a standard switch. We create those port groups, we configure our VLANs, our teaming policies, etc. at that point. So we have, on here we have a blue port group and a brown port group, which are configured and pushed down to the effectively the distributed switch, which is now configured on every host. Now there's an important new port group function for the people who are new to VDS. That is the uplink port group, or the DV uplink. Now the important point to mention here is that if you are configuring, like this picture here, where we have a host with just 2 NICs, 2 physical network cards, then it's fairly straightforward when we say we would have our uplink port group has 2 uplinks. Yeah? We connect 2 uplinks. But it's important to realize that if you have maybe servers with 6 uplinks or 8 uplinks, 8 NICs in them, then you have to set your VDS at the vCenter level with effectively the highest common denominator. So therefore, if you had a server that had 8 NICs, you would configure your DV, your virtual switch, with 8 uplinks. Okay? The fact that you've only configured 2 and only used 2 inside a DV uplink port group is just the way it works, okay? So we have to make sure that any uplinks that are not in use are configured as unused. So don't create an uplink and not plug it in, but then give it to the distributed switch, okay? So if you've got an uplink, you must use it if you've configured the switch. Important things, again, management versus I/O plane. So all of the management of the distributed switch is held within vCenter. All of the I/O function, all of the switching, packet switching, is actually held inside the vSphere host. So you don't need to worry about loss of connectivity if you lose vCenter. So if you lose vCenter for any reason, your switch will continue to function. You will just lose the access to create new port groups, provision virtual machines onto a distributed switch port group, etc. Okay, until your vCenter comes back up, but it won't affect traffic. Okay, so let's look at some of the new features. So with 5.5, we've introduced an enhanced LACP, which we'll talk about a little more in the next slide, and also Venki will cover a little bit more about that. Anybody heard of enhanced SRIOV, or anybody heard of single root IO virtualization? Okay, this is for workloads which need really low sensitivity or low latency requirements. So if they need nanosecond latency requirements, you can look at SRIOV. And with 5.5, we've enhanced the ability with SRIOV to be able to push those settings within the port groups, such as VLAN tags, etc., down to the SRIOV card. Okay. We've also got Mellanox support for Mellanox 40 gig support. So if you need 40 gig, you can now do it. There is a specific card that we support to give you 40 gig into the host. Okay, so gone are the days of pushing hundreds or 10 network cards into a host to give you that access. We now have 40 gig support. New feature as well, packet classification. So as well as being able to do layer 2 traffic marking, we can now do DSCP, layer 3 marking as well in QoS. And also we can do some traffic filtering as well. So we can actually now drop packets. We can do basic ACLs within the distributed switch. And then a new feature which is available both on the VDS and the standard switch is host level packet capture, so TCP dump. So if you have to, it's very useful for being able to capture what's exactly going on inside the host. So you can go onto the host and you can do a command line utility, TCP dump, get the information back about what's actually going out of each NIC. And you can do that at different levels. So you can do it at the physical network card level, NIC level, you can do it at the port group or the port level, and you can do it actually at the VM kernel level as well. So if you want to look at maybe VXLAN traffic and how that's encapsulated, you can see all of that traffic. So it's really helpful in a VXLAN environment. So anybody using VXLAN, by the way? No? Anybody looked at VXLAN? A few people, okay. Okay, so as well, LACP. If we are using LACP or you're looking at using LACP, then we've increased the capabilities of LACP. So LACP that we have, link aggregation control protocol, is based on standards. So it's based on standard. 802.3 AD. It's the important thing to know about LACP is that there is a handshake that goes on effectively between the VDS and the physical switches. So the physical switches have to be configured for LACP, and then the two communicate to keep things in check. So what we allow you to do now is, or what happens really with LACP, is that you can aggregate your bandwidth and you can provide redundancy. And if any part of the system fails, if an uplink fails, then the handshake or the heartbeat going between the physical switch and the DVS will update that to make sure that that NIC isn't used. Okay? And it also detects cabling mistakes, etc. So, now, some of the enhancements in the previous version of 5.1, we only had support for one lag, one aggregation group. In 5.5, we have support for 64 lags per VDS and per host. So you've got a lot more scalability. Some of the feedback was that we didn't have enough scalability across the lags. And then importantly as well, there has to be an algorithm for hashing in terms of load balancing. So when you have these teamed NICs, you have to have some way of load balancing that, and that's based on an algorithm. We now have 22 algorithms that you can use, 22 hashing algorithms for the teaming. Okay, so finally, before I hand over to Venki, we'll just talk about customer deployments. So we've seen quite a number of deployment options for VDS, but what we've seen in the past is maybe one VDS per cluster. So maybe if you had 3 or 4 clusters in your environment, customers would build a VDS for cluster 1, a VDS for cluster 2, and a VDS for cluster 3. Now, with where we've moved to with the VDS and the scalability, with being able to go up to 1,000 hosts, there is really not any requirement to do that. And actually, probably the most beneficial way of installing it is to have just one VDS if you can. So stretch one VDS across all of your clusters. But we do have the ability to separate them as well. And we can have hundreds. As I said, we can have 1,000 VDSs. So you can have the same number of hosts inside a single virtual distributed switch as you can in vCenter. So we support 1,000 hosts. Now the other thing really is that when you start looking at centralized management, if you have robo sites or offices, branch offices, then you can still centrally manage the VDSs across multiple sites. So typically, if you have multiple sites, you would have a VDS per site. And there is a white paper that you can get from us that talks about the latency requirements or latency issues between the management plane talking to the VDS. Remember, the I/O plane is completely separated. So it's not going to affect I/O, but there is a management latency in terms of pushing the configuration down to each host. And the last thing I'd say about this is really that if you're looking at comparing us with some of the other products out there that you can use, now we've got really feature parity with the other distributed switches that we can plug in. And we've got scalability that way exceeds all of that. So scalability-wise, it's we can add 128 across 1,000 hosts. You shouldn't have any scalability issues with the VDS. Okay, and the final thing really is role-based access. So with VDS, you can implement role-based access as well. So that means that if you have administrators or network people who want to manage the network side of things and your VI admins do the deployment of virtual machines, then you can separate that admin as well through role-based access and role-based authentication. Okay, I think that's me about done. I'll pass over to Venki, and then we'll have a time of question and answer at the end.
Thank you, Dan. Okay. So after looking at the new features and the capabilities of the distributed switch, what I'm going to do is I'm going to talk about the design best practices, because one of the things which typically comes up in terms of discussing the design best practices is that since VDS can scale across so many different hosts, how do I go about designing this? Because there are so many features like network I/O control, for the traffic management, as well as the load-based teaming and all that stuff. Where do you use it? When does it make sense? So what I'm going to do is I will go through these 5 different categories. So whenever you take a design exercise, you have to think about what is your goal in terms of designing. you might be considered about reliability. Like, I want to make my design reliable so that if there is a failure of host, what happens to that? From the vCenter point of view, you want to think about, okay, if my vCenter is failure, I'm going to lose the management capability, but am I okay with that? If you are not, then you have to think about multiple vCenters and all that. But from the connectivity point of view, I'm going to focus on how do you design your distributed switch and how do you connect to the physical network. We'll talk about that. Then comes the security. So security is typically, if you talk to government and other industrial sectors where they really want physical separation of their traffic, I think those really have some advantages. That means you can separate the traffic, but at the same time you are losing the flexibility of moving things around, because when you are tying one traffic type to one physical NIC, you have some limitations there. I will talk about how you can do security through VLANs and also the private VLAN capability that we have on the distributed switch. From the performance point of view, as you are doing higher consolidation ratios, you are seeing that a lot of traffic is generated from the virtual machines. And you want to see that if multiple virtual machines are running on the same host and you have some important virtual machines, like important application, which needs a particular bandwidth, and you want to make sure that that particular application gets that bandwidth. So we'll talk about the performance, how you can use this network I/O control feature and provide the right bandwidth to your applications. From the scalability point of view, Dan already mentioned, so one correction I want to make there is that one VDS can support 500 hosts, but across vCenter, if you want to have 1,000 hosts, you have to have 2 VDSs. But the scalability is there, so we will talk about that, how do you scale in terms of port groups and number of ports also. Finally, the operational aspects. I think some of the guys raised hand about network team, and one of the key concerns for the network team is how do I get visibility into the traffic? When you look at the host where you have suppose 10 virtual machines, you really can't see the traffic onto the physical network when the virtual machines are communicating with each other on the same host. So we have the capabilities such as port mirroring, we'll talk about some of those, as well as NetFlow, which allows you to monitor the traffic and send it to a collector tool. Because that is also important in terms of how you operationally look into this distributed switch in terms of operation and management stuff. Okay, so let's get started on this. So one of the things which is important to understand is what is the factors which you have to look into when you start designing. First is what type of servers you have. So how many of you are using blade chassis servers in your environment? Wow, it's almost more than 50% people are using blade chassis designs. Okay, so the type of server matters, because in the blade chassis specifically, you have might be 210 gigs. If you are using Flex 10 or Cisco UCS, you might have that capability of doing traffic management on the blade chassis and presenting multiple NICs to the server. And we will talk about that, because that is one of the important factors how you design with the distributed switch. Then physical switch capability. When you look at how you connect your distributed switch or to the physical network, you have to think about whether you have the capability such as link aggregation control protocol on the physical switch. There are designs where some physical switches support this MLAG capability, like multi-chassis lag. In the Cisco terms, it is called VPC. How many of you are using VPC or MLAG? Okay, there are like around 10 people. So that also matters. So whenever you are thinking about designing, you have to make sure that what is the capability on the physical switch. And especially network guys are going to say that, okay, I want to do LACP. Then you have to make sure that the distributed switch is configured for LACP. What I'm going to do is, when I'm going to describe this design best practices, I'm going to take an example deployment with the 210 gigs, but it will apply for the normal 1 gig also. But since blade chassis is very common, the 210 gig deployments are very common nowadays. So do you agree with that? How many of you using 10 gigs really, using 10 gigs? Yeah, see, I think it's like most of the people are now going for 10 gigs, so I think it makes sense for us to just focus on that. Okay, so the 5 parameters which I talked about earlier, first let's take it reliability. and take a look at how you connect your distributed switch to your physical network. And this is a very old way of doing connections to the physical switch. If you look at this example, you have a host with two 10 gig NICs, and you are terminating directly on one physical switch. You have some port group configuration up there on the VDS, where you have options of choosing port ID hash, which is the default teaming algorithm. You also have option to do MAC hash, explicit failover, and load-based teaming. Remember here, there is no LACP here because you are directly connecting these two uplinks to the physical switch. The problem with this design is this is a single point of failure, because if your physical switch goes down, your VMs lose connectivity. So this is not a good design. The other option is then you terminate your physical next to two different switches. So this is much more reliable design, because now if one physical switch fails, that uplink to the VDS will fail, and the virtual machine traffic will be moved to other path on the other uplink. Now in this case, again you have the same option, the teaming options, where you do load balancing based on port ID hash or MAC hash or explicit failover. And I will talk more about how load-based teaming works. The load-based teaming term is not there as part of the port group. It is called route based on, I think, link utilization. That's what it says when you look at the drop-down menu of the port group. Okay, the other option which you have is if the network team says that I have configured LACP on the physical switch, you have to make sure that your, no, not LACP, sorry, this is Ether channel. How many of you using Ether channel? Because Cisco switches support Ether channel, which is a static, it's not LACP, it is a static Ether channel configuration where there is no negotiation going on between the distributed switch and the physical switch. When this configuration is there, you have to make sure that port group is configured for the IP hash configuration. Remember that first two options don't recommend IP hash. The third option, where you configure the Ether channel on the physical switch, then only you make sure that IP hash is configured on the port group there. So finally, we have this deployment where some people, as they said, they are using MLAG or VPC, where the two physical switches act as one logical switch, and it gets connected to the distributed switch. In this option, you have LACP configuration, as well as you can use IP hash. Some of the configuration I have seen customers making sure that there is an Ether channel configuration on the physical switches in this mode, and they configure IP hash there. But you have option of LACP as well. As Dan mentioned, advantages of LACP are that if you misconfigure like the connection between the physical switch ports, it can be detected automatically, because now distributed switch is communicating with the physical switch and negotiating that. And if there is some misconfiguration, we detect that and then make sure that your traffic flows accordingly. So looking at those connectivity options, important thing to really highlight here is that avoid any single point of failure. Don't connect all your uplinks to one physical switch. Then when you configure your port groups, make sure that depending on what you have configured on the physical switch side, make sure those the hashing algorithms are configured properly on the port group. Then from the physical switch point of view, we have some requirements in terms of configuring BPDU guard and port fast. So this is a standard practice. It's been around for a long time. When server ports are connected to physical switches, the physical switch port typically doesn't participate in the spanning tree protocol. So how many of you are really familiar with the spanning tree protocol? A few of you. So I don't want to go in a lot of technical details there, but what happens in the spanning tree protocol is it detects loops in the network, and it goes through a process of detecting loop. It has a block state and allow state and all that stuff, which takes a long time to converge. Typically on the server ports, the ports where you have servers connected to the physical switch port, you don't have to run spanning tree protocol. That's what it's doing with this BPDU guard and port fast configuration, where you don't run all the spanning tree protocol and the server ports immediately get connectivity to the network. The final one is trunk all port group VLANs. I will come back to here, I think explain that, what exactly happens here. So this is a diagram where if you look at this two servers which are connected to two physical switches, you will see that the switch port here is configured with port fast, BPDU guard, and you will see that VLAN 10 and 20 are trunked on that particular switch port. The VLAN 10 is configured on that, I don't know what color is that, orange or brown, orange port group, and the green port group is VLAN 20. So when you have multiple port groups, you can do isolation based on VLANs. So you can have one VLAN configured on one port group, another VLAN configured on another port group, and you can have these VMs isolated from each other. So the VMs which are connected to that orange port group cannot talk to the VMs on the green port group unless traffic has to go out on the physical switch and get routed. So that is the advantage of creating VLANs in your environment on the distributed switch side. Okay. I talked about the best things about LACP, but there is one downside which I want to mention here for the link aggregation control protocol. So link aggregation control protocol depends on this hashing algorithms. So you have like 22 hashing algorithms which you have for this link aggregation control protocol. If you have a deployment where you have web servers and you have like a lot of users coming into the web servers, you have this variation of IP source and destination addresses. So you have a lot of variation there. And when you take a hash output of that, you will get load balancing, which is kind of distributed evenly across two links. But if you are, suppose, a storage access happening from a virtual machine to a storage array, where there is no variation, like IP source and destination addresses are kind of same, because you are mapping your IP source and going to a destination which is storage array, which doesn't vary. So your hashing algorithm doesn't give you variation such that you will load balance the traffic across two physical NICs. So understanding what is your workload, what is your traffic pattern is very important. The load-based teaming, so why load-based teaming is better? Because load-based teaming, what we do is we take the utilization of the uplink into account. So if you have two physical NICs, if one of the physical NIC is using, suppose 8 gigs of bandwidth, and other physical NIC is using only 1 gig of bandwidth, we detect that. We detect that and we figure out that now I want to move some of the traffic which is flowing to that physical NIC number 1 and move it to another, which LACP cannot do it. LACP is really based on hashing algorithms which will be fixed. You might have some scenarios where all the traffic is hashed to one physical NIC. In those scenarios, load-based teaming is going to add more value here. Important thing to note here is that load-based teaming doesn't require any special configuration on your physical switches. You don't need any special configuration there. So let's take a look at how does it work. So we're going to take an example here where we have 3 different traffics, vMotion traffic, virtual machine 1, and the virtual machine 2. Based on the normal hashing algorithm, which is the port ID hash, what happened is the vMotion is going through the physical NIC number 1 on the left here, and the virtual machine 1 traffic also is going on that. If you combine those two traffic, it is like 12 gigs of traffic, 7 plus 5, but you have only 10 gig available here. But if you look at the virtual machine 2, which is going on the physical NIC number 2, you have only 2 gig traffic flowing through that physical NIC. So what load-based teaming does is it detects every 30 seconds, it goes and looks at the bandwidth utilization and then makes the decision that I want to rebalance the traffic. So when it rebalances the traffic, it looks into the utilization of the physical NIC and also looks at what is the traffic required for that particular virtual machine or other traffic which is flowing. Then decides what is the optimal bandwidth distribution there. So in this case, what happened was the virtual machine 1 traffic was moved to the physical NIC number 2, and now you have even utilization. So this is really taking into account the utilization of the physical NIC, which LACP cannot do. So we recommend you using this only for virtual machine traffic or vMotion traffic. I will talk about why you cannot use this for iSCSI traffic, because iSCSI have port binding and all that stuff. But definitely when you're thinking about virtual machine and vMotion traffic, you can think about load-based teaming as an option for that. After looking at reliability, let's now focus on the security side of things. How do you get security in your virtual environment with the distributed switch? So this is an example where your host has these type of traffics. In your case, it might be different. Here I'm showing virtual machine, NFS, FT, management, vMotion. You might have some other traffic such as iSCSI, or you might have fiber channel. But the point of this diagram is your host has all these different traffic types running on them. And you want to make sure that they are isolated from each other. You don't want your virtual machine traffic seeing the management traffic, for example, or any virtual machine seeing other NFS traffic, because everything will be visible and then you will lose the security part of things. So what you do typically is you create VLANs for that particular traffic type. Sorry, actually so what I created here, the port group, for each port group here, port group A, B, C, D, E, you have different VLANs configured. So VLAN is a mechanism to do isolation between traffic types. So provide traffic isolation with VLANs. There is a default security settings on each port group, and we would recommend you to keep it like that, because one of the thing is that promiscuous mode, which is really allows you to send traffic to all the ports, is reject, as well as the MAC address change, which suppose you have a MAC spoofing kind of thing, where a virtual machine comes up and then assumes a different MAC. That traffic will not be allowed to go out, because we don't allow MAC address changes. Similarly, the forge transmit will not be happening. So security features are already inbuilt on the port group configuration, and we would recommend you to keep it the same. We do have the PVLAN configuration. How many of you are using private VLANs? 2, 3, almost 20 of you. So one of the important things to understand from the PVLAN configuration is you can create these isolated, I think promiscuous, and these private VLANs, and then you have to make sure that the physical switch is also configured for that private VLAN configuration, because unless you do that, the PVLAN setup is not going to work. But it allows you to isolate within a VLAN multiple different users. Suppose you have 2 applications, and you wanted to you had only one VLAN configuration available. So you can create these PVLANs and then isolate these 2 applications from each other using that. BPDU filter. I talked about this BPDU guard feature on the physical switch. Means you have to enable BPDU guard on the physical switch. The BPDU is Bridge Packet Data Unit, which is only used for spanning tree protocol. Now, when you configure port fast and BPDU guard on the physical switch, what you are telling the physical switch that you will never see any BPDU packet from the host. That's what you are telling that physical switch configuration. But if you have a suppose compromised virtual machine on that host and it starts sending the BPDU frames, what will happen is the physical switch is going to block that port, saying that I was not expecting any BPDU on this port and I'm getting it. So I'm going to block that port. Then what happens is the server is going to move that traffic to another uplink, and another port is going to get blocked. So this is a denial of service attack kind of scenario where your compromised virtual machine is sending BPDUs and you are losing all the hosts in your environment. To prevent that, what we have done is we have a BPDU filter capability on the host, which allows you to filter packets like BPDU packets which are coming from virtual machine. The distributed switch never sends a BPDU packet because it doesn't do spanning tree protocol. So only scenario this can happen is when a virtual machine is compromised, and that does that. Finally, we have access control list. This is a new feature in 5.5 which allows you to filter packets. So suppose you want to do like for a particular virtual machine, say give access to only one server or outside world, then you can filter the traffic for a particular virtual machine by giving these filtering capability allows you to filter at the MAC address level or IP address. So if you are really interested in looking in this feature, hands-on lab is a good example where you have the capability where you can try this out. So we looked at the reliability aspects and the security aspects. Now let's focus on the performance. So why do we care about performance? So as you are looking at this 10 gig deployment where you have, suppose, 10 virtual machines running on one single host, you might be getting into a scenario where your 10 gig pipe is getting filled because you are running vMotion, you are running virtual machine traffic, you are running NFS traffic, all the traffic going through this 10 gig pipe. And you are deploying these new business critical applications such as database servers or voice over IP applications. You want to make sure that these applications get the right amount of bandwidth because you don't want them to get impacted by vMotion process, for example, because vMotion is a very bandwidth intensive process. If you are, suppose, trying to move 2 or 3 virtual machines from one host to another, it might take as much bandwidth as is available to it. So if you have a 10 gig bandwidth, it will try to grab as much bandwidth as possible. And that is one of the noisy neighbor problem. That means if vMotion is happening, your voice over IP application or your database server application is going to suffer. You don't want to have that kind of situation where vMotion is impacting other traffic. So these scenarios, it is important to go and do network I/O control, and I will explain how network I/O control works and how you can use that. So this example here, again, going back to 2 10 gig interfaces, and this is a host where you have vMotion, management, FT, and NFS traffic. So you will see here there is a shaper layer and there is a scheduler layer. Each physical NIC has this shaper and scheduler. And I will talk about what shaper does and what scheduler does. As you can see here, vMotion traffic is flowing through this physical NIC, and all other 3 traffics are flowing through this physical NIC number 2. Now, if you add a virtual machine traffic, for example, now in this case, what is happening is virtual machine and vMotion traffic is flowing through the same physical NIC. And this is kind of a scenario where vMotion can take as much bandwidth as it can, and then it can impact the virtual machine traffic. So what do we do with that? So in the network I/O control, you have the capability to define the shares and limit. This is exactly similar to what you have been doing with the CPU and memory resources, where you have shares for giving the CPU resources to a virtual machine or the memory resources to a virtual machine. Similarly, what we do is for your traffic type, here we have 5 different traffic types, and you have the capability to provide shares and limits to those traffic types. So what I've done in the first, suppose you focus on the first 2 rows, the virtual machine traffic and vMotion traffic. I have given virtual machine the share as 30 and vMotion as share as 20. There is the shares is a relative. It's relative importance of that particular traffic. So what I'm saying here is that virtual machine traffic is important than the vMotion traffic. Now the first question comes in, what does this share do? What happens with this share? How does it translate into bandwidth? So this is the calculation for the bandwidth calculation here. So we take 30 plus 20, which is the 50 shares, which are going through that physical NIC number 1. So total shares available on that physical NIC are 50. Out of that, 30 is allocated to the virtual machine traffic. That means you have 6 gig of traffic for virtual machine and remaining 4 gigs for vMotion. This happens only when there is a contention. That means when vMotion is trying to pump traffic as much as it can. Similarly, virtual machine is trying to pump traffic as much as it can. In that scenario, that scheduler layer is going to make sure that virtual machine traffic will always get 6 gig traffic, and vMotion will always get 4 gig, not more than 4 gig. But if there is no vMotion going on, if vMotion was not there, virtual machine can get all the 10 gig traffic. So that's the flexibility of using shares configuration, where you can say that I want this share number to be higher for a particular traffic type, and then what happens is that if that traffic type is not utilizing the bandwidth, that shares are provided to other traffic types. So it's not fixed bandwidth for each traffic type. There's the other parameter, which is the limit parameter. In this case, if you look at it, the limit parameter is not configured. But suppose you configure a limit parameter. Limit parameter applies at the shaper layer. So as you see here, I'm limiting the vMotion traffic to 4 gig. So the shaper layer, what it is going to do is, when he sees vMotion traffic more than 5 gigs, suppose, the shaper is going to drop the extra 1 gig traffic. So it is never going to make it to the physical NIC. So the downside which I see with this limit approach is that even if bandwidth is available, the vMotion process cannot take advantage of that bandwidth. So, but there are some customers, for example, service providers, who want to make sure that their users, one of the users, suppose, one of the paid users, they want to limit some of the traffic for them. They can use this capability to limit the traffic. But it is not really recommended to use that limit parameter always, because, as I said, even if the bandwidth is available, you can't use that, because the packet drops happen much before the scheduler layer. Okay, so another capability which we have with the network I/O control is, I talked about this multiple application scenario, where suppose you have two applications, application 1 and application 2, and they have different bandwidth requirements. What you can do is you can create a user-defined traffic type. So there are standard traffic types which are available, but you can define your own traffic type. So in this case, what I have done is I have defined application 1 traffic type and application 2 traffic type, and then I allocated shares for that. Another thing which you can do is this quality of service tagging, 822.1p. And I will talk more about that. Why do you need that? So we have the capability to tag the traffic where you say that this traffic is important, and the network, physical switches in the network should treat that traffic according to the priority. So what are the different tagging capabilities? So there are two tagging capabilities. One is called class of service, which is the layer 2 tag, and another one is the DSCP marking. The DSCP marking is introduced in 5.5, where you can do the layer 3 tag also. So when you look at a packet header, when you look at the layer 2 header, the class of service is a 3-bit field. So you have 1 to 7 values. Whenever you tag a traffic to 7, that means it's important traffic. When you don't tag it, that means you don't care about that traffic type. So that is the class of service field there. Now in the DSCP one, you have 6 bits. So you can have 64 different types of tags which you can program on that particular packet. So we have both the capabilities now. If you want to use class of service, because you are using physical switches, understand that class of service field, then you can use class of service tagging, or you can use DSCP marking, which is typically the physical routers and switches do take a look at the DSCP tags and then prioritize the traffic. So I'm going to show you an example. What are the different options you have to do the tagging? So one option you have is your application itself does the tagging. So in this example, what I'm showing here is the application which is running on the host, like voice over IP application. They do the tagging at the DSCP level. Then that flows through all the way to the physical virtual switch. Virtual switch will pass on that tag, and then it will go out on the physical network here. The problem with this approach is that now administrators lose the control, because I don't have any control as an administrator, and everybody will make sure that their application is tagged higher so that they get more bandwidth in the network. So this is not kind of a recommended approach which is available, but you can think about that. The other second approach, which is much more recommended, where you have administrators have control over this tagging capability, where all the tagging decision is done at the virtual switch level. So in this case, this is the preferred option. You have a single place where you can do the tagging, because you know which traffic I want to prioritize, and you make sure that you do that at the distributed switch level. There is a third option for the network folks who have been doing this, where they have been doing tagging at the physical switch level, where they can start tagging at the access layer switch there. The downside for this approach is that now you're missing all the quality of service or bandwidth reservation in the host. So you're not getting the end-to-end quality of service. That means you are not tagging the traffic right at the source of the traffic. Always remember that doing things at the source of the particular traffic type is much more important, because in that middle layers, you make sure that all the virtual switch does the make sure that tag is properly managed and it gives the right amount of bandwidth for each traffic types. This is a quick example in terms of what happens in the physical network when a tagged packet goes out. So what I'm showing here is that the green arrow is a higher tagged packet, and the red arrow is lower tagged traffic, and the gray arrow is not tagged traffic. If that traffic goes out on this particular physical switch, you see that physical switch is congested now, because it is getting all the traffic from different ports, and the traffic is going out on one physical switch port. In this scenario, the physical switch, since it's oversubscribed, it is going to drop traffic. So it is going to make the decision of drop based on the priority of that particular packet. It is going to make sure that the green arrowed packet, which is higher tagged, is never get dropped. And you will see that that packet goes all the way to the application out there. So this is the end-to-end quality of service. So first thing you want to make sure is that your application gets the right amount of bandwidth on the host by doing network I/O control. Then you make sure that you tag the traffic such that the physical networks treat the packets according to priority. If you don't do that, your application traffic might get dropped on the physical network, and you will have lower performance for that application. So make sure you do end-to-end quality of service and take advantage of the class of service and the DHCP marking. We also have the capability to do per port traffic shaping, and I'm not going to go into more details, but you have the ability to control a particular port, virtual port, where a virtual machine is connected, where the definition of ingress and egress is different here. So ingress traffic is with respect to that virtual port. Suppose you want to control a virtual machine traffic which is going out. What you have to do is you have to define an ingress parameter. So the ingress parameters which you have, ingress and egress parameters, is average bandwidth, peak bandwidth, and burst size. So these three parameters allows you to control that particular port. If you want granularity in terms of traffic management, which network I/O control cannot do, then you can use this port level traffic management. And this parameter is at the port group level. So you can go to the port group level and then provide these parameters, ingress and egress traffic parameters. So just an example here. So we have a token bucket kind of design here, architecture, where when you configure your average bandwidth, which is this green line here, if you see here the initial time, this virtual machine is sending less than average traffic. What happens in that case is there are some tokens which gets accumulated, because you are not utilizing all the resources which you reserved it for. But then you can have the capability to do a burst of traffic here. Typically, IP traffic is bursty traffic, and that's why this particular algorithm makes sense here. So this is what you can do at the port level if you want to go at that granularity and do traffic management at the port level. Okay. Another thing which I think want to mention here is that I mentioned the load-based teaming does not work with the iSCSI multipathing, because iSCSI, if you want to use higher bandwidth for iSCSI traffic, you have to go for multipathing solution. And then MTU configuration is one of the options there. For vMotion, if you need higher bandwidth, what do? We have this feature called multi-NIC vMotion. You can use that if you want higher bandwidth for vMotion. Here also load-based teaming doesn't help, because vMotion bandwidth is not going to be split into multiple physical NICs. So one of the questions which I always get is, will LBT is going to help in this scenario? It looks like I have 10 minutes. Okay, so I got to rush out. So these are these slides are going to be available for you. So take a look at that. But these are the kind of best practices in terms of vMotion and iSCSI. And finally, I'm going to talk about the scalability stuff in there. So how do you scale your environment? So either you scale your environment based on whether you are adding new clusters, means you are adding new hosts or new clusters in your environment. We talked about that distributed switch supports 500 hosts across one distributed switch. So you can keep adding more clusters in your environment. If you reach to 500 hosts and you wanted to add more, you can create another distributed switch and then add other hosts on that particular distributed switch. So there is no, in terms of scale, you really don't lose anything in terms of when you go for the distributed switch. You can keep on expanding your environment. Now, another type of scaling which you might be thinking about is like VDI deployment, where you have multiple users, a lot of users, and you think about virtual ports, how many virtual ports I have on a distributed switch. You really have 10,000 port groups. That means you can have isolated port groups, 10,000. Unfortunately, you don't have that many VLANs. You have 4,000 VLANs, so you really don't get a real advantage of doing that many port groups. But number of virtual ports, if you look at it, like 60,000. So you can connect 60,000 virtual machines in your environment. And a recommendation is you use the static port configuration on the port group instead of using the dynamic. I think dynamic is still available, but we don't recommend you to use that particular port configuration there. Okay, operational aspects. I talked about some of the things which I briefly mentioned, that NetFlow feature is there, port mirroring features are there. So whenever you want to monitor your virtual machine traffic, you can use the port mirroring capabilities. We have RSPAN, SPAN, and ERSPAN capabilities. I think for vSphere admins, this might be new terms. For the network admins, these are kind of common capabilities that they have been using on the physical switches. We also have host-level packet capture tool, which Dan mentioned about that. So that is there. We also have the capability called network health check. How many of you are using network health check? Have you heard about it? Network health check feature? Okay, few of you. So what network health check does, it detects misconfiguration between the virtual switch and the physical switch. There are 3 parameters which really are important: VLAN configuration, teaming configuration, and MTU. If you misconfigure VLAN on a port group and then you don't properly configure the same VLAN on the physical switch port, the network connectivity is not going to be there. So this network health check feature detects that misconfiguration, and it's pretty important feature, especially for the vSphere admins and the network admins if they are 2 different teams. And network guys says, oh, I have plumbed this configuration. You go and figure out what is happening in your environment. At least you will get a warning on your vSphere, on the vCenter side, saying that this particular VLAN is not configured. And you can go back to the network guy and say, okay, this is what it is. You go and configure that VLAN. Okay, so quickly on, as Dan mentioned, VDS is a next step for your network virtualization journey. Means you have to have VDS before you think about NSX. And NSX has these different layers where you have data plane, control plane, management plane, and all. Data plane is where the distributed switch lies there. And there is another session at 2 o'clock which we will talk more about NSX if you want to get more details about that. Distributed switch also supports VXLAN. I think few of you are using VXLAN, but this is kind of technology overview. I'm not going to go in detail here because I don't have time. So, but this is what the VXLAN picture is. Distributed switch is important for VXLAN because standard switch does not support VXLAN. And key takeaways finally is VDS is flexible. It can meet your design requirements in terms of reliability, scalability, security, and performance. So make sure you use those features. It simplifies your network because you have one virtual switch to manage throughout your environment. Make use of network I/O control and load-based teaming feature. And VDS is the key component for the NSX platform. And for more details about each of the features, you can go to the blogs at blogs.vmware.com, and you can follow me on Twitter. And these are the sessions, and thank you, and fill out the survey and questions. So there's a mic there. I think if you have any questions, you can come by later, or yeah, I can ask there. Thank you very much.